NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto was once regarded as a legitimate planet in the solar system. It is still a captivating and perplexing dwarf planet. Despite its proximity to Earth, its previous classification, and the most recent bold assertions by esteemed astrophysicists Neil deGrasse Tyson and Michio Kaku, new interest in Pluto has been sparked. They have suggested that Pluto, an ice-covered planet, could be on a trajectory toward a devastating encounter with Neptune. This has triggered a flurry of inquiries regarding the consequences and plausibility of such an event. Could this scenario be an exaggerated theory, or is there proper cause for concern? Let's explore the potential ramifications of an initial Pluto-Neptune collision. Pluto was initially classified as a planet. However, due to its irregular orbit, it was later reclassified as a dwarf planet, a decision that has maintained Pluto as a topic of ongoing discussion in the world of astronomy. Leading scientific studies now suggest that Pluto's orbital course poses a danger as it coincides with Neptune's, raising concerns about the possibility of a fatal impact. Given their proximity in their respective orbits, can a collision between Neptune and Pluto actually happen? If so, what would be the implications for Pluto's path? There is nothing quite like Pluto's orbit in our solar system. It spans a complex 248 years, meaning that since its discovery in 1930, Pluto hasn't even completed one full orbit yet. However, the peculiar nature of Pluto's orbit doesn't end there. It follows an elliptical path that deviates significantly from the near-circular orbits of most other planets. To complicate matters, Pluto's orbit is tilted 17 degrees toward the ecliptic, making its inclination much steeper than that of other planetary paths. One especially fascinating aspect of Pluto's orbit is its relationship with Neptune's. Approximately every 20 years during Pluto's lengthy orbit, it comes closer to the Sun than Neptune, a strange anomaly that raises the crucial question: why haven't Pluto and Neptune collided? The answer lies in powerful gravitational forces exerted by other celestial bodies. After Pluto was discovered, astronomers acknowledged the peculiarity of its orbit. Unlike the nearly flat orbits of other planets, Pluto's steep angle and elliptical trajectory set it apart. As researchers studied it further, they realized Pluto's orbit actually crosses Neptune's. Despite these unconventional characteristics, Pluto's orbit has remained surprisingly stable, thanks to the gravitational effects of other celestial bodies. Celestial mechanics, particularly the three-body problem, helps explain the interactions and movements of Pluto, Neptune, and the Sun. Pluto's path through space can appear erratic, and even the smallest initial changes can drastically affect its long-term trajectory. Yet, simulations have demonstrated that Pluto's orbit has remained stable over extended timescales. This indicates that its path, despite its chaotic appearance, is balanced by the gravitational pull of massive planets like Jupiter, which plays a crucial role in stabilizing Pluto's orbit over billions of years. These forces help preserve the overall order of our solar system and prevent unrest during Pluto's orbit, a fascinating balance between order and chaos. Still, predicting celestial movement, especially of objects with irregular orbits, is inherently difficult. While numerical simulations offer useful insights, they also emphasize the unpredictability of space events, making long-term predictions uncertain. The concerns raised by astronomers like Kaku and Tyson about a potential Pluto-Neptune collision may seem far-fetched, but their warnings have caught public attention. If such a collision were to happen, the consequences could be detrimental to the solar system. The impact would release a vast amount of energy, likely leading to Pluto's destruction due to its diminutive size and icy composition. The resulting debris could endanger nearby planets and moons, including Earth. The effects of a Pluto-Neptune collision wouldn't be limited to Pluto alone. For Neptune, it could significantly alter its orbit and atmosphere, depending on the nature of the event. Michio Kaku, a renowned theoretical physicist, provides a unique perspective. His extensive research into string theory and celestial mechanics suggests that understanding Pluto's orbit could yield valuable insights into the physics governing space exploration. By examining the gravitational interactions shaping Pluto's orbit, we can gain essential knowledge for future space missions. This science could help us prepare for potential threats from space and assist in the exploration of far-off regions of the solar system and beyond. The fundamentals derived from Pluto's orbit also have wider implications for research into other dwarf planets and trans-Neptunian objects. Pluto's complex orbit challenges our understanding of planetary motion, showing us how dynamic and unpredictable the cosmos can be. The connection between string theory and the mechanics of the universe emphasizes the importance of understanding how planets and celestial bodies interact. In the event of a Pluto-Neptune collision, it would be a defining cosmological event, offering a rare opportunity to investigate string theories under extreme conditions. Such a collision would release immense amounts of energy and could provide insights into the behavior of fundamental particles and forces at high energy levels, which are central to string theory. Despite the minimal direct impact on Earth, due to our distance from the outer solar system, the scientific implications would be profound. This event would provide new opportunities to study the fundamental nature of the universe, especially in areas relating to string theory and theoretical physics. Pluto continues to captivate the imagination of both astronomers and the public alike. Space enthusiasts and the ongoing debate. Despite the fact that it is a dwarf planet, Pluto has rekindled interest in its function in our solar system. The problems raised by Kaku and Tyson emphasize the intricate forces that control the movements of celestial bodies, emphasizing the importance of understanding orbital and gravitational influences. These forces are essential for comprehending the mechanics of the solar system's dynamics and the ongoing debate surrounding Pluto's status as a planet. Pluto's steep and elliptical orbit defies conventional models of planetary motion. In contrast to the nearly circular paths followed by neighboring planets, Pluto's orbit intersects Neptune's at specific points. Throughout its extended trip around the Sun, the gravitational forces exerted by planets like Neptune have played an important role in keeping Pluto's orbit relatively stable over the centuries. Despite this, predicting how celestial bodies will act in the future continues to be a challenging and uncertain task. The possibility of a collision between Pluto and Neptune serves as a reminder of the inherent unpredictability in planetary dynamics, although such an event appears extremely remote in the near future. The gravitational interactions between Neptune and Pluto illustrate the delicate equilibrium that exists within our solar system. Pluto's study offers important lessons for the future of space missions, assisting researchers in exploring other distant bodies and gaining a deeper understanding of planetary evolution. NASA's New Horizons mission, launched in 2006, delivered groundbreaking photographs and information about Pluto and its moons during its historic flyby in 2015. This mission disclosed fascinating data about the vast areas of Pluto's surface, including water ice and expansive frozen nitrogen plains. These findings help us learn more about the processes that shape this distant world. The success of New Horizons highlighted the technological advancements and collaborative efforts required to reach the farthest edges of our solar system. Through research on Pluto and its moons, scientists gained invaluable insights into the diverse conditions and bodies found in the outermost parts of the solar system. These discoveries have profound implications for future missions to explore other distant dwarf planets and trans-Neptunian objects, providing scientists with critical data about Pluto's formation and evolution. Pluto's transformation into a dwarf planet has sparked significant discussions regarding how we define celestial bodies within our solar system, reflecting broader questions about scientific classification and the nature of evolving knowledge in astronomy. Understanding Pluto's orbit is crucial to gaining insights into the mechanics of space and planetary dynamics, especially as we venture further into the depths of the solar system. By exploring Pluto's interactions with Neptune and other celestial objects, we continue expanding our understanding of planetary formation and development. Discoveries and ongoing research have substantially contributed to our comprehension of planetary motion and the development of the region known as the Kuiper Belt, located beyond Neptune, where tiny icy bodies reside. Understanding Pluto's orbit provides valuable clues about the gravitational interactions that may have shaped the early solar system, essential information for future missions focused on exploring potentially habitable worlds beyond our solar system. Despite the extremely low likelihood of a Pluto-Neptune collision, the study of such objects serves as a reminder of the universe's ever-changing nature. As we continue to explore beyond the borders of our solar system, the study of planetary orbits and celestial mechanics will remain central to our efforts. Pluto's unique orbit offers instructive examples of the planet's complexities and the forces that have shaped celestial motion over time. The investigation of Pluto's orbit and encounters with Neptune reminds us of the erratic yet patterned nature of the cosmos. With every new finding and theoretical model, we enhance our comprehension of the universe and gain insights into the enigmas of distant worlds. The study of Pluto's orbit not only provides answers about this remote world, but also helps us predict future trends in celestial behavior, improving our understanding of the factors that control our solar system and beyond. In conclusion, the possibility of a collision between Pluto and Neptune, though highly unlikely, underscores the dynamic nature of the universe. The study of Pluto's orbit and its interactions with Neptune's gravitational forces offers valuable insights into celestial mechanics. As we continue to explore these distant bodies, we refine our models of planetary systems and improve our ability to forecast future cosmic events. The potential for discovery in this field is limitless. As technology advances, so too will our ability to study and comprehend the vast and ever-evolving universe. Exploration of Pluto's position in the solar system will continue to shape our understanding of the cosmos for years to come. Pluto's orbital behavior and its distinctive interactions with Neptune have long fascinated the scientific community. Despite being a dwarf planet, Pluto continues to challenge our comprehension of planetary dynamics. The fact that Pluto's orbit crosses Neptune's at various points without causing a collision demonstrates the complex nature of gravity and celestial mechanics in our solar system. One of the most intriguing features of Pluto's orbit is its resonance with Neptune. This resonance, known as a 3:2 orbital resonance, means that for every 3 orbits Pluto completes around the Sun, Neptune completes exactly 2. This synchronized relationship ensures they never get too close to one another, even though their paths intersect. Pluto and Neptune are essentially engaged in a cosmic dance, with their orbits set in such a way that they will never collide. This gravitational relationship is an excellent illustration of the precision and balance of celestial mechanics. The forces produced by Neptune's gravity on Pluto, and vice versa, work together to maintain orbital stability for both. Without this resonance, Pluto's orbit could have been disrupted, potentially leading to a collision or other significant changes in its path. Astronomers rely heavily on understanding this interaction because it sheds light on how celestial bodies maintain equilibrium, even when their movements appear chaotic. Additionally, the Kuiper Belt, the region beyond Neptune, is a treasure trove of dwarf planets and icy bodies. Pluto is the largest known object in this belt. Its orbit provides useful information about the conditions that prevail in this distant region of the solar system. Kuiper Belt objects, KBOs, and trans-Neptunian objects, TNOs, are remnants of the early solar system. Studying them allows us to peek into the conditions that existed billions of years ago during the solar system's formation. Space agencies like NASA are now directing missions to explore these remote areas. NASA's New Horizons mission, which conducted its 2015 flyby of Pluto, provided us with unprecedented images and data about Pluto's surface and atmosphere. The mission's findings revealed towering mountains of ice, frozen nitrogen plains, and a variety of weather systems, indications that Pluto is a geologically active planet. It also offered insights into the diversity and evolution of Pluto's moons, shedding light on moon formation in. The New Horizons mission demonstrated the growing capabilities of modern space exploration. Such missions not only enhance our understanding of distant Pluto-like celestial objects, but also lay the groundwork for more ambitious research into the Kuiper Belt and beyond. The mission's success has rekindled interest in exploring these far-flung regions and could inspire similar missions to other Kuiper Belt objects. Despite the apparent stability of Pluto's orbit, its tilted and eccentric trajectory raises questions about the long-term dynamics of the solar system. The fact that Pluto's orbit deviates significantly from the nearly circular orbits of the 8 major planets presents a fascinating puzzle for astronomers. The inclined and elliptical nature of Pluto's orbit suggests that the solar system may not be as orderly as it appears at first glance. The chaotic behavior of Pluto's orbit could have profound implications for our understanding of planetary formation and evolution.